Okay guys, in this video segment we're going to take this idea of electron configurations and we're going to give a shortcut for that. Okay, so I'm assuming that if you're writing electron configurations that it's not your favorite thing in the world to write 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6 over and over and over and over again. Okay, I know I enjoy it. I think it's a very exciting time of my life. However, I'm guessing not so much for everybody. So what chemists have come up with is a way to shorthand this. And what we do is we basically use the noble gases as kind of like a benchmark or a stopping point within that, okay? So what we do is instead of writing out the entire configuration, we actually start with the normal configuration and then we break it down to the noble gas. So let's use tin as our next example here that we see on the screen to do that. So here we go to the board. So if I have tin, Sn, first thing I'm going to do is I'm going to find it on my periodic table, and I'm going to locate tin, and there it is, number 50, and I'm going to work backwards. So 50 working backwards. The noble gas that is previous to that is krypton. Okay, so tin is going to be the same as krypton. Okay, and what we do is colon, space, bracket, bracket, put the Kr in there. So we're saying that tin is exactly what krypton would be, and then we just add in the extra stuff, okay? So besides krypton, after krypton, it would be a 5s, 2, and then remember we drop down, so it's a 4d, 10, that goes all the way across, and then 10's the second one in, so that would give me a 5p2. Okay, so this notation, while it's not hard to do, it gives us a couple different advantages. The number one is it makes things shorter. Okay, so it's easier to write. Now, the second thing is later on in the year when we start dealing with chemical bonding, most of this chemistry actually deals with these outer electrons right here. Okay, so it actually causes us to ignore all the stuff that's on the inside and gives us a chance to focus on those outer ones. Okay, so that is noble gas configuration. Go ahead and pause the video here. There's several more that you can do for practice. Notice how argon is your next one. Now, you can't be super lazy. You can't just use argon in brackets to describe argon. Okay, you need to go backwards by one. All right. Go ahead and practice these, and then when you're ready, go ahead and hit play again, and I will show you the answers to these to make sure you're doing them correctly. Okay, so here's our answers then with these now. So if you notice, specifically for argon, we go back to neon, to the previous noble gas, and then fill that out as before. Okay, so here's your examples of these. You can check those out. We're going to keep going in this video, and we're actually going to talk about the exceptions to our octet rule now. Okay, so there are two different groups that we want to identify for exceptions. There are others, but these are the ones that you're responsible for in terms of being assessed for the exception. It's group 11 and group 6. Okay, now what happens is sometimes the Aufbau principle and Hund's rule conflict. Okay, remember Aufbau principle says high to low energy, and Hund's rule says do it the most stable possible way. Well, there are some scenarios where it's actually more stable to put things in a little bit higher energy levels. Okay. So who wins? Okay, in the world of chemistry, does energy always win or does stability win? Okay, and the reality is it comes back to stability, because energy is only one piece of the puzzle, where stability encompasses multiple different things that together make the atom as stable as possible. So in this case, Hund's rule is going to win, and we are going to work with the most stable configuration. So we do have some exceptions to the filling pattern that we would normally have according to the Aufbau principle. Those exceptions come from the fact that if we have a full orbital, an empty orbital, or even a half full orbital, that those are areas of stability. So sometimes we'll shift a few electrons around to get an orbital to be full or half full. Okay, empty orbitals, those sometimes happen when you ionize. We'll get to that in our next segment. Okay, so let's take a look at, for example, copper, because copper is one of our exceptions. It's in group 11, and kind of see what happens to that. So what we're going to do is we're going to take copper, and we'll do its noble gas configuration. So copper is argon, okay, in brackets, and it would be a 4s2 3d9 according to the normal Aufbau rules, okay, normal filling pattern, okay. 4s2, 3d9. Now here's a problem. 9 is not quite full. S is full, but 9 is not. So this is a pretty unstable thing for copper. So what happens instead is this does not happen. Instead, what copper does is, again, it still is like argon, but it's a 4s1, 3d10. Okay? Now the benefit of this is now that d orbital is full, but the s orbital is still half full. So because we get a half full and a full orbital, this is much more stable than a full orbital with just missing it by 1. Okay? So this happens with all group 11 elements. So not just copper, but it also works with silver, gold, rhodogenium, all the way down that group. Okay? So what happens to them is exactly the same pattern, where they don't end up with an S2D9, it's an S1D10. Okay? Now the same thing happens with group 6. In group 6, though, if we do, let's say, chromium, chromium is just like argon, again, and 4s2, 3d4 is what it would be. With chromium, again, we're not quite half full and we're full, so by not doing this, instead doing 4s1, 4s1, 3d5, they're both half full, okay? Which is a more stable way of doing it than if we just had one full and one not quite there, okay? Again, that happens in our group 6. So chromium and molybdenum are the only two that you're responsible for. Actually, once you get below molybdenum, we get some f orbital stuff, interference, and things change again. So we don't really want to talk about that, all right? So these exceptions you are responsible for, okay, in terms of knowing them. There are others, but they don't pattern out really well, where these work really well because it's all group 11. It's the beginning ones of group 6. The reason behind it is the same because we're trying to fill an orbital by taking something away from that s orbital, okay? And we always do just take one out of the s, move it over to the d, and then that way either we can fill or half fill that orbital, okay? All right, so those are exceptions. We're going to end the video here, and then in our next segment, we're going to talk about ions and how you do electron configurations for ions. Thank you.